All right, section 1.1 is called Mathematics and Problem Solving. And the first thing I want to introduce you to is the four-step problem solving process. And you may have seen these before. Different textbooks put them in a little bit differently. But this book talks about number one step as understanding the problem. So understanding the problem may or may not include all of these things, but it could include a lot of different things. So talking about stating the problem in a different way. Do you understand what the problem's asking? What is it that you need to find? What do you need in order to find that? What are the things that are unknown? What information are you given in the problem? And then what information are you given that maybe you don't need, or information that you need and you don't see given? Okay? And those are some different kinds of questions you may ask yourself as you're reading through the problem. The second step is to, after you've read through the problem and understand what's going on, is to figure out how are we going to solve this? What's the plan going to be? We're going to look in particular in this section at a variety of these different strategies. They do not all work for all problems. That would be silly. It really would. But there's usually a couple of different ones that when you look at the problem, you're like, oh man, I think this strategy would work really well here. So we're going to see those different kinds of problems. So this is not exhaustive. This isn't the only list ever created or anything like that. But this is a list of some really good ways to attack strategizing, problem solving, when you're sort of looking at the problem originally and saying, okay, how am I going to do this? So one method is to look for a pattern. I love patterns in things. I think it's great. My kids did it the other day. I don't remember what they did, but I was like, oh my goodness, look at you. You just did a pattern. That's fantastic. And so patterns are great. They help you to remember things. I have a brother-in-law who is a medical doctor, and he remembers his pattern for his home alarm visually, right? So he has this image of his keypad, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a keypad, just like on a standard telephone, right? And he doesn't really remember the numbers. He remembers the location of it. It's a pattern that he remembers from the location. Another option or another possibility would be to examine a related problem and see if you can use that before. You've done that before. That's what happens when I was telling you that in section B of your homework, if you want to figure out how to do the problem maybe, you might look at section A and look at the back, right? It's a similar problem. Or you might look back in the section and look and say, oh, did they do an example that's like this? And you say, oh, look, here's how they did this example, and it's kind of like my problem in this way. Doesn't have the same numbers, doesn't have exactly the same context, but I can apply that method. That's what you're doing when you're doing that strategy, part B. C, examine a simpler or a special case. So if you're doing something that's true for like 100 people, maybe you look at 5 people and say if you can figure out what's going on with those 5 people and then sort of generalize it for the 100 people. That would be the example for that one. A table or a list. Do we have any list makers in the class? Yeah, me too. I like tables and lists. I can usually see patterns if I write them down in a table or a list. So I kind of use those hand in hand sometimes. Identify a sub-goal. Sometimes there's problems you have where you have to get to one step, and once you have that information, then you can move on. So sometimes if you can figure out, okay, can I get to this point? I mean, like, I don't know how to get to the whole problem, but can I get like part of the way there? A sub-goal of what the problem's looking at. How about diagrams? Anybody like diagrams when you're looking at problems? Depending on the problem, they can be very helpful to draw. So there are some times when drawing a diagram is extremely helpful. And if it isn't helpful for you, it doesn't necessarily mean that it's not helpful for little Johnny in your class who thinks that way. So it's a good thing to actually think about in terms of our visual learners as well, even if that's not you. Working backwards. I'm sorry, I missed one. Guess and check. Guess and check sometimes feels like cheating to people. It isn't if you're organized and you think about the way you're using the guess and check strategy appropriately. I'll show you an example of that one. Working backwards. People work backwards a lot when you look at the homework and you look at the answer in the back and you say, how did they get to the answer negative 32? Oh, look, I see a negative 32 in the problem, which means they did this first, as their last step, and then before that they must have done that. Working backwards can often be a very good strategy as well. And then the last one, writing an equation. Sometimes that's helpful and sometimes it isn't. It also depends a lot on the kind of mathematics you're using, whether an equation makes sense. You're teaching 3rd grade, probably not appropriate. You're teaching 6th grade, 7th grade, it might be. So it depends on the type of problem that you're using as whether an equation might be helpful. All right, once you've figured out how you want to try and solve the problem, you actually have to try to solve it, right? Does that make sense? So you're going to carry out the plan. So you're going to figure out the step from step 2, the problem or the method that you wanted to use to solve the problem. You have to attend to the precision in the language that's being used. So if it asks you for something, you need to make sure you're actually answering the question that's asked and not some sort of other question that's going on. And I'll show you an example where people make that mistake in one of the examples we're going to do. You should check the step along the way. This can be done formally or intuitively. Okay, so formally is the idea where when you're done with the answer, you take the answer and you plug it back into something to make sure it works. That's a formal way of checking a solution. Informally sort of means, like, does it make sense? Because if you told me that this mom had 3.5 babies, you got problems. Okay, so does it even make sense for the particular problem that you're looking at? That's the informal sort of question that you should ask yourself on any particular problem. And you should keep an accurate record of your work. You can use scratch work when you're working problems, and that's great. But you should be able to look back at the scratch work and figure out where you went next. So even your scratch work having some sort of a progression to it so that you can see it would be helpful. That way, if you made a mistake on, like the third piece of what you were doing, you can go back and fix that mistake all the way through the problem instead of having to erase everything and start all over again because you don't know what you did. All right, last thing is to check your work to decide if the answer is reasonable. That's the whole question I was sort of looking at with the 3.5 babies, right, for mom. No, she doesn't have 3.5 babies. That doesn't work. She either has 3 or 4. All right, last thing then is to check the accuracy in the original problem, and that's what I was talking about plugging something in to make sure it actually works in the context and in the equation maybe, or in a table format that you were working on. All right, so what we're going to do in the rest of this section is we're going to actually look at these different problem-solving strategies, give you some examples of how they're used, and try to sort of see ways that we could maybe identify how a problem might fit into that category and use this this type of a model for solving it. All right, so the first one we're going to look at, example 1, is Gauss's problem. Gauss was a mathematician, and he was actually 6 years old, first grade, when he actually came up with this strategy. So if you have Gauss in your classroom in the future, God bless you. I hope you're prepared. He's very smart, and he was very intuitive in how he approached problem solving. So this is an example. He was in early grade school. He was in first grade, and the class was given an assignment that was supposed to take him a lot of time, because I'm sure you will never do this when you're a teacher. Of course not. But the teacher needed a break to be able to get something else done. So she told the students what she wanted them to do was add up the numbers from 1 to 100 and find the total amount. And if you can imagine actually doing this by hand, 1 plus 2 plus 3 plus 4 plus 5 for a little first grader, maybe second grader, this should take them quite an amount of time, right? It didn't. Gauss actually found it almost immediately, and I'm sure the teacher was just crushed that whatever it was she was trying to get done was not going to happen because he found the answer so quickly. So I'm going to actually show you how he did it using patterns, okay? So here's what he did. Okay, all right, just a second. All right, so the first thing that he did is we're going to see about how he did it, is we're going to write down the numbers like this. So we're writing out all the numbers that he's supposed to add together. So far, so good? No big deal. And this would work for no matter what numbers we were doing, right? It doesn't have to be 1 to 100. If it were 50 to 67, we could do the same thing. And then what we're going to do is we're going to actually pair them up. And we're going to pair them up in such a way that we pair the first one with the last one, the second one with the second to last one, the third one with the third to last one, and so on. What happens when you add 1 and 100 together? You get 101. What happens when you add 2 and 99? And 3 and 98? And this will continue, correct? So you can take the first number, the last number, pair them together. You're always going to get 101 in this particular problem set. So you're going to have a whole bunch of 101s that you're adding together. So what we're going to actually do is we're going to call this S, and we're going to say then that we're going to replace we're going to replace all the numbers in this value with the number, whoops, missed one, 101. So I'm replacing every number in this sequence of numbers with the number 101. Now, that should be a little disconcerting because that's more than I had before. By how much? How much more is this than the first 1 plus 2 plus 3 plus all the way up to 100? Now notice what I did. I replaced the numbers 1 and 100, both of them, with the number 101, right? So this right here, 1 turned into 101, and this number 100 turned into 101. This is not 50, but you're getting really close. Well, it's twice as much more. This is twice as much as I had before. Because you see, before I had the numbers 1 and 100, which add to 101. And now I replaced the number 1 with 101, and I replaced the number 100 with 101. That's twice as much as I had before. Because I replaced each of the numbers with that sum that I sort of did by using these pairs of numbers. It's twice as much as I had before. Now, I still don't know that I want to add 101 plus 101 plus 101 a whole bunch of times. Is there a faster way to do that sort of addition? How? Multiplication, right? That's the whole deal of what multiplication is. When you get to 3rd grade or 2nd grade or wherever they're doing it these days with all the changes that's happening in our public school systems, the whole point of multiplication is it avoids us having to add a number together a whole bunch of times, right? I mean, I don't want to add 3 plus 3 plus 3 plus 3 7 times. I just want to do 3 times 7 is 21. That's what's going on here too. But in order now to do this, I've got to figure out how many 101s I have, right? All right, so let's take a look back here. So I've got this 2s. I've got a whole bunch of 101s, and my question is, how many of them do I have? Well, look back at the original one. I don't have 200 of them. Look back at the original one, because I've got as many 101s as I had original numbers. I had 100, right? Because I started at 1 and I ended at 100. So there's 100 numbers here. Does that make sense? Right? If I call you number 1 and you number 2 and you number 3, then there's 3 of you because I started with 1 and I ended with 3. So there's 100 numbers here. And this is fabulous now because I can do this with very simple arithmetic. What is 100 times 101? 1001. Hang on. 1010, right? I'm still not getting the right number. What does it should be? About 10,100. That work? I'm going to add 2 zeros to the end. But I didn't really want to find out what the sum doubled was. Because right now this tells me double my sum is 10,100. So what do? I divide by 2. Okay, I know you don't see it right now. I promise it's still on here. Somebody tell me what happens when you take 10,100 and divide by 2. What do you get? 5,050. So the sum of the first 100 numbers is 5,050. Okay. But it sort of feels a little bit funny because, well, what do I do with that? How can I extend that idea to do any sum of numbers? And that's example 2, which we'll do next time.